Hello everyone, this is Hyunjun. So I am a very fresh graduate PhD student, PhD doctor from TU Munich, and my topic was usually about 3D computer vision in a really broad range, like 60 pose estimation, depth estimation, grasping, or human avatar in the reconstruction, etc. But today, what I want to talk about is something that is not very fun thing. It's about the data set. It's something that people do not really want to talk about it, but they like to use it. Before going into the details about my talk, I want to have a very smart question session with you, with your experience, especially for 3D vision people. So, have you ever had a time that your network produces really good results, very good results, and it's even better than the ground truth? But because of the ground truth has an error, like you can see the artifact in the ground truth, some errors, and then evaluation result is not very good, and then you cannot convince your reviewer to accept your paper, and then you get rejected. Do you have any experience like this? No? Yeah. What about a little bit better side? Let's say you can clearly see issues in your network. You can produce some artifacts and errors, but luckily, your ground truth has the same error. So you have a really good accuracy, and you frame it, and then you get a good numbers, and you sell your paper as a breakthrough, and you publish the paper, and then your professor is so happy about you, but deep inside of you is very guilty because you know that your network is not as good as it looks or as is advertising your paper. Have you ever had this experience? Yeah, so I call it as guilty pleasure, but this is the best thing for a computer vision field. But yeah, so this kind of experience usually happens because 3D computer vision data set is annotated in a little bit different manner compared to 2D computer vision case. For example, let's say you have these cute puppy images, and if you're doing 2D computer vision, annotation you may have to do something will be very simple. Classify the image, dog, or getting a 2D bounding box. You can just press 4 dots and then you annotate really accurate manner. Segmentation can be a little bit tricky, but you can zoom in and pick everything pixel by pixel, and you have good accuracy annotation of the 2D case. So, however, when it comes to 3D computer vision, annotation becomes very challenging. For example, what if I give you 10 euro and ask you to annotate the surface number of the dog per pixel? Is there anyone who can do that? If you can do that, please let me know. I can hire you for my dataset annotator. But these things are very hard. It can get really worse. Like maybe you want to annotate the per pixel depth of these puppies from your camera center. You don't even know your intrinsic, so you can't do that. Well, what about the 3D meshes? Or I can also go wild, like I can ask you to give you a rotation and translation of the dog from the canonical orientation from your camera center. So this kind of annotation is very required in 3D computer vision, but unfortunately, as a human, you cannot really annotate just by looking at the images, not like 2D computer vision. So what we do here is usually using 3D sensors or using a cold map, the greatest invention ever for 3D computer vision, or maybe you can use synthetic tools, including the gaming engine. But all of these methods has some drawbacks, like 3D sensors has artifacts and human cannot fix it. I mean, you try to fill the hole in your 3D, but it's not going to be super accurate anymore. Cold map up to scale, it's sparse, it can be noisy. Synthetic data, you may not be able to produce very realistic noise, so you will always suffer from the sim to real domain gap. So all of these combined, it makes our life as a 3D computer vision researcher very hard. So this is what I want to talk about, the 3D vision computer data set. So I prepare my presentation into 3 chapters. First, I'm going to motivate you a little more and show example of my early research career from 2019 or 2021 and show how the ground truth affected my work And then I am going to show some of my work that focus more on the getting accurate 3D ground truth, including using the robotic arm or external tracking camera. But you see, it's not going to be very pleasing to watch someone annotating with these tools. So I also presented some better topic that is more about how to get away with human labor and produce a good data set, but using the diffusion model. So I'm going to present some of the texture augmentation technique we are trying to work on it, or data-driven approach for the synthetic noise generation, or some cool idea how we can make a diffusion-based full RGBD data set. So we can start with my personal experience. So my research career started from the 60 pose estimation problem. It was one of the early work for render and compare based pose estimation, where you are given with the initial 60 pose and the mesh, and you render into the RGB and you overlay that, and then you just feed these overlaid images into the network, and your network iteratively update the pose until you have a better fit. And you can see the result looks quite cool, especially judging from this is from 2020. And this kind of the work, you cannot train the network with the real data set because you're not able to obtain the intermediate ground truth for each step. So what I did was training everything in synthetic manner. So my goal was very simple. Do whatever you want and then give me the best pose you can get so that you can overlay the rendering into your RGB. So this was my goal, but when I started to evaluate my network, I found this was not a good idea because the ground truth you will look in the real data set is very off. You can see if you render the mesh with the ground truth into the RGB image, you will see some offset like here and here. It can be like go up to a few centimeters. And so unfortunately my accuracy was not very good and I couldn't convince my reviewers, so I have to skip this project at the end. So this was my first experience. And my second experience was a little bit better. So it was about RGB and depth fusion, and depth was coming from the raw signal from the TOF. And then my task was to fuse these two data with some network intermediate alignment and produce a good quality depth as output. And luckily, I learned my lesson from my first project. So I did a fully supervised training, and surprisingly, the result was almost 40% better than the baseline. I published my first paper in a 3DV as oral, so it was a really great outcome. But then, when I look at my results as a video, if you look at here, the results, it's not very great. You see everything is very blurry. There's flickering going on. It has some artifact. Well, this is not so good. Maybe you don't want to use it in your real life application. So, well, this is because the ground truth I used for training and evaluation was coming from the real sense, which is one of the most popular depth sensor, especially for providing a bad quality depth. So, yeah, so you get the point. So the problem I found in my early stage of the research is about the data set. The ground truths in the public, they're not very reliable. So if you're unlucky, you will produce a really good result and then you get penalized by ground truth. Or if you're lucky, your network is going to produce the artifact and then you will get a good numbers and you can publish paper. And you can see the irony here. So as a really young and motivated PhD student back in 2020, I decided to solve the problem by me suffering and providing good quality ground truth so that we can make everyone happy. So that's how I started some of my research that is especially focused on the 3D computer vision data set. So I can show you two of my examples. First we'll be starting from the robot, and second will be more extended version of it. But yeah, so first I decided to use the robot for annotating tool because robot has a forward kinematics and all the joint has a different angles, and this end effector pose you can get from the robot is very accurate, especially you're using the industry level robotic arm like this. You may be able to get a really good accuracy and repeatability in the end effector pose. So we luckily had this one in our lab, so I decided to use it to annotate the object and the camera pose so that I can have a good quality ground truth from the camera. So this is some of the teaser. So you can see the annotated ground truth rendered into the RGB looks very accurate. It's even including these photometrically challenging objects like glass or reflective surfaces, which were considered to be the worst nightmare ever for the annotation people. And then I extended the work to annotate the background and the furniture so that I could render everything as a depth and provide it as a depth ground truth. So let's talk a little bit about how I made it work with the robotic measurement. So it comes with the two different parts. The first part is about using a robot and measure the surface and then annotate and recording the camera view. And the second part is more engineering task that is just doing something to annotate the background, which I'm going to skip. So for the time, I was just going to show you just how I managed to measure everything with the robot, because this was the core contribution in this paper. So it was very simple. So as you can see from this drawing, we measure something. So it's good to have a 3D mesh. So we first scan everything with the 3D scanner. And then for the challenging objects, we have something called 3D scanning spray, which you can spray on the object. It's going to make everything white and evaporate in 2 hours. So you have enough time to scan that. And then for the background and furnitures, I used the 3D handheld scanner to produce a good quality mesh. So once everything is ready, I just exploit end effector here by attaching the tooltip and do the pivot calibration, and then calibrate it so that wherever my robot point, I can get a really accurate 3D points from the robot base. And then I just glue all the objects into the surface, and then I measure the surface by 20 to 30 points. And then with everything, points from the mesh and the 3D measurement, you can get a point correspondence and ICP and get a good quality annotation from the robot like this. So after this one, everything was very straightforward. I could just attach camera to the robot and do the calibration so that I know the camera pose. And then I could just make the data possible. For example, you can see the result here. I usually do the qualitative evaluation by visualization, by rendering the stuff into the RGB, and you can see the rendered mask or rendered depth fits perfect to the RGB. And we also added different sensors, and you can see the sensor quality here is not so great, and you got my point of the ground truth is not great in the field. So I came up with some idea to measure the accuracy, and it was very good, like 0.8 millimeter. I think this is still the best one you can find in the vision field. But if you look at this data, visualization, you may ask one question: why are your camera trajectory so weird? Why it just go back and forth? Well, it's because the robot has an issue with the joint angle, so you cannot go too much angle because it's going to break. So there was so many issues I found using the robot. So I decided to extend this work with the external tracking device because it's a little more flexible. So what I did was very simple. So I have a robotic arm, but I swapped this hardware with the external tracking device. And just one simple thing. So I use end effector pose for annotation tool, but now I use the pose from these tracking balls as an annotating tool. And it has advantage of more annotation area, and you can go more crazy with the camera views and less limit on the workspace. But of course, you have to take care of the accuracy in the pose, because I wanted to do this work because I want to get a good quality annotation, right? So I swapped the main hardware for the pipeline from the robot to the tracking body, and then I had to add something called trajectory refinement step, which It's a very simple approach. So if you go from A to E, you will end up with some initial annotation that is sometimes a little bit misaligned, sometimes very accurately aligned, etc. So I just selected manually a few frames that is very accurate and then ran a call map. And why did I fix the camera pose into some samples? Because if you do that, the call map is not going to destroy your scale. That means it's going to refine your camera pose, but you don't have to worry about your scale anymore, which I think is a really great deal. So I can show you the result. You can see that before the refinement, there was a little bit off because maybe I was moving a little bit too fast with the camera. But at the end, everything got solved by running this extra refinement. Yeah, so with this setup, we have now the better looking trajectory. You can see my camera can go crazy with different angles and sometimes jittering so bad, but you can see the quality of the annotation here is very stable that you can use my data set without worrying about issues. And then the quality was not as good as robot, but comparable and still better than the state-of-the-art data set you can see on the left side. Yeah, so with this setup, we published a really great paper called How to Get 60. It has 3 to 4 times more scenes than before, and many frames, different annotations, many objects, viewpoint coverage, and different modalities. This was our dream post data set. But you can see that we changed the hardware, and then we managed to have a much better data set. But to make these 41 scenes, I had a really hard time. For example, I was working around maybe 80 hours per week for 3 weeks in a row, and you can see how poor Seoul is suffering for this data set. But yeah, so the point is you can do something to reduce the workload for the data set, but at the end you may have to do something. And this is not great for the scaling up for the large models nowadays. So at the moment, the lesson here is that incorrect ground truths can mess up many things, and you can put the human being into the annotation loop to improve the quality of the data set, but it's time consuming and it's really hard to scale up. So someone is gonna suffer by doing this. So you will ask question, then is there any way to scale up this one and we can do this without human labor? So that's why we decided to do a little more into the diffusion model. So right before my defense, I was a little bit too bored and I was high on the energy drink. So I decided to ask ChatGPT how the Red Bull factory looks like in Austria. And you can see the video looks very realistic. So realistic, you will believe in that Red Bull is organic product, right? But the problem I want to tell you here is that diffusion model can give you really realistic, image. You don't have to tell them about, how the lighting is going to look like, no 3D meshes. Just give something and it's going to generate something very realistic. But there's a drawback. You can see there's something shady going on, like there's no consistency in the shape, so you can now ask me a question. You wanted to do this because you wanted to have a good ground truth, but if you use this, you're going to mess up something. So that's right. So now question is how to make the data generated is feeding into your 3D information. So we decided to do something simple. Let's do some image generation task for the 60 pose estimation network by doing a texture augmentation. So this is how the real data looks like usually. You have a meshes, you have a ground truth pose, and then you have a real image, and you have a depth map. This categorical pose estimation network always requires depth because you have to generalize in a new object, and you have to take care of the scale. So we always have a depth. So our idea is very simple. Let's just generate the RGB image that follow the shape of the real image as a texture augmentation, and then let's just try the post estimation network and see how it works. So our approach was very simple. So given the object and the ground truth, we just place the object in the rendering software and render the shape, and then extract the canny edge, and then give it to the diffusion model with some prompt, and it generates the image that follows the geometry of your ground truth, which is really great, right? So for the network training, it usually works like this. The network usually takes the depth, but it's masked by the ground truth. So you can see that only having a texture generation is already enough. So we just added this as an extra augmentation data and then trained the network. And then the result was quite interesting. So how we trained this new same network as before, but new data was having around 30K the real sequences and 30,000K generated sequences. So we just generated the 100% word scale. So we have now 60,000 images. I mean, you can see the result of the quality of the rendering is not so great sometimes, but it already improved the result quite decent. And if you look at this, the hardest metric, we managed to just provide like relatively 10% or 20% better than the just using with the trainings, and only with the 30,000 images extra. And we could just generate unlimited amount. But here's a limitation. Here, this is only about the texture generation. So if you want to form the new scene, you cannot, for example, change the orientation of the object. You always have to follow the original orientation and the shape of the scene, which may not be a good choice. This is because one of the drawback here is that, one of the problem here is that the synthesizing the noisy sensor depth is a big blocker here, because you saw this network always take the depth input, and if you cannot generate a realistic depth, you're going to suffer from the domain gap in the depth, so you're not going to perform better than just original data set. So there were some way before how to synthesize a noisy depth, usually by the simulation. For example, Blender Pro, they argue that they make some simulation of the stereo matching and produce very realistic sensor noise for the stereo image. But if you look at the real stereo image, you cannot really beat this quality of real sense with the simulation. So, or what about more physics-based sensing modality like TOF? So this is one of the methods. They use more simulations with the ray bouncing and ray tracing. They did many things to produce the noisy raw signal for the TOF images. But if you look at the real TOF images, this is how it looks. This is very different, right? And it gets worse. So when it comes to these challenging objects, these simulation cannot really deal with all the scattering with the different materials. So you can see simulation is not a great choice to generate the noisy sensor in this case. So I decided to go again with the diffusion model because it's very cool. So I just made a very simple prototype. This is just a latent diffusion model. It has an encoder decoder with the noisy depth, and then I trained the encoder, and then I just make now it's a noise addition. So I made a noise addition, and my guidance is just coming from the foundation depth and scaled from partial ground truth from the depth rendering of the object. And surprisingly, within 2 days, I was able to get a really good, realistic looking noisy sensor depth just by dumping one of the depths. This is very cool, right? Yeah, so now what we're doing at the moment is how to set up the scene better so that we can have a full diffusion-based RGBD data set for the post-estimation problem. So now we have a real mesh you can just download from the web, and then you can generate the layout of the objects, and then you can also augment the meshes if you want. And then with these layouts, you can render the normal like before, and then you get the generative RGB, and now we can put these into the monocular depth estimation pipeline and predict the depth. And then we scale it with the rendered depth map here, because scale is really important. And then we we go through the depth diffusion model and produce a good quality depth. I mean, very realistic noisy depth. So now with this setup, you can easily get a full synthetic data set that is quite realistic, that is composed with different combination of meshes and some synthetic layout of the object, and the most important, the realistic RGBT scenario here. So this is what we are doing at the moment. So we are trying to first improve the quality of the RGB, because this RGB generative model, so there are one that you can pay for it, but they're expensive if you want to generate the 100,000 images. So we are trying to use the open source model, but getting a good quality RGB is not super great at the moment, but we are trying, and also we are trying to make this depth diffusion model a little bit better, so that it produces the better, it represents the better noise statistic of the real scenario. Yeah, so I think great future work in this direction could be first training the generative model to produce extra sensing modalities, depth, TOV, LiDAR, whatever you want, or you can also generate maybe thermal imaging, so robotic ultrasound. You just need to have a big data, not really annotated, because diffusion model can help you out. And then you can apply this into the many different existing model and just improve the accuracy by training again with the more data set. You know, I can, like I showed you, 60 pose or many different applications like robotic, SLAM, grasping, etc. can be get helped by this one. Or you can also generate your own edge case data set to tackle the problem. And what I think is really great will be applying this into the robotic simulation, because I found many of the simulation for DLA or AI agent, they usually take the perfect depth and RGB or just RGB. But I think it would be really great to train such network and then feed into your agent training in reinforcement learning or VLA, etc., so that you can already have a sense of what will happen if you put specific data set into the training loop. So yeah, this is what I prepared for my talk. If you have any question, let me know.